Hi everybody, we're in lesson 9. This is our last lesson in unit 1, modeling with functions for pre-calculus. Let's jump right in. You know, we have in real world settings, we need to create and construct functions by using the vocabulary and assigning variables and symbols to the independent and dependent variables. So we're going to explore 7 or 8 examples related to that. We'll start off rather easy here. Let's say we have the perimeter of a rectangle and it's a garden, and that perimeter is 84 feet. And we want to write the area as a function of the width of the side. So when I think about a rectangle, I know that the area is length times width. And in this case, we have perimeter. We were given perimeter. So perimeter is 2 lengths and 2 widths. If you think about the distance around, we've got a length and a width and a length and a width. So 2 lengths and 2 widths gives us the perimeter. But they've also given us that the perimeter is 84, so we can substitute that 84 is equal to 2 lengths and 2 widths. And then if we divide by 2 on each term, we would have 84 by factoring out the 2 on the right and dividing through by 2. Our 84 would be reduced to 42, and 42 would be the length plus the width. So the length, they want us to write the area formula as a function of width, which means we need to isolate length and name length in terms of width. So the length would be 42 minus the width. This gives us a name for the length, and we're going to write the area in terms of width, and area is length, so we're going to use this 42 minus W, that's our length, times the width. So the area formula in terms of the width would be 42W minus W squared, using the distributive property. So that's pretty easy. Let's work on the next one. This one is a volume formula. The volume for a right circular cone is 1/3 pi r squared h. And if the height is twice the radius, we know height is twice the radius, and we want to express the volume as a function of the radius. So that's telling me volume in terms of radius. What is that formula? So we need to get rid of this h and substitute this value or this expression for h. So volume is 1/3 pi r squared times h, but we're substituting 2r. That gives us a formula for volume in terms of radius. Get an extra space here. Nope. Nope, can't do it. Okay, so we'll just write it out to the side. The volume in terms of radius is, I'm going to multiply this, pi r squared times the 2, and times the r would give us 2 pi over 3 r cubed. A formula for volume in terms of radius. Then here we can either use our calculator or just simplify and give an exact answer. So find the volume of a paper snow cone cup whose radius is 2 inches, because our snow cone cup would be a right circular cylinder. You know what snow cone is? Frozen ice, yummy. It's summer. I'd love some. The volume, when the radius is 2, is 2 pi over 3 times 2 cubed. So that volume would be 16 pi over 3 cubic inches. And if you don't have a good feel for 16 pi over 3, we can jump over here to our calculator and let it evaluate that for us. Look, what happened? We need 16 pi divided by 3, and that's like divided by 3. and that's going to give us about 16.755. So our volume, and the radius is 2, is about 16.755 cubic inches of delicious snow cone ice. Okay, that's not bad. Now we're going to look at some business and economic problems. I know on the AP exam they've started asking similar questions in context to business for business calculus. And we want to look at some terminology related to business, like the revenue. Revenue is the amount of money that you bring in for selling X number of units at some retail price. So that formula would look like that. And in economics, there's a rule called the law of demand. It tells us that the price and the units are related. That's pretty straightforward. If one item, one variable increases, then the other is going to decrease. So if you increase the price, you're going to decrease the number of units sold, and they're related in that way. So here's our first example of that. The demand for tickets to a local water park is given by this equation, and P is the price of the ticket in dollars, and X is the number of people who plan to go to the park at that specific price. So we want to know what price would provide an attendance of 3,000 people. So this is our X, the price that would generate if we wanted 3,000 people to attend. So we got to use our calculator here. We've got 75, nope, it's, oh, I'm on my screen here. Sorry about that. I need to be over here. 75 minus 200 times 3,000 people in attendance. And that would be a $15 ticket. So if you wanted to run this water park and you needed to have 3,000 people attend every day, the best price would be $15 per ticket sold. Now, what is the total revenue at that ticket price? So you could do one of two things. Revenue, excuse me, is X times P. So you could write an equation for that, which is part C, write the revenue function. So the revenue function is X times P, and P was 75 minus 200 X. So that would be 75X minus 200X squared. That would be the revenue function. But in part B, it's really just as easy as saying, I've got a $15 ticket and we're having 3,000 people attend, and I've got a $15 ticket. So that would be $45,000. So X was 3,000. And the ticket price was 15. So we could expect a revenue of $45,000 on a daily basis if our tickets were $15, and that would attract 3,000 people. Then in a general setting, you could use this equation down here to calculate revenue for any other number of people attending the park. Okay, let's try a little bit more complicated business question. So let's say we've got a skateboard designer, and they've got a fixed monthly cost of $9,202 and a variable cost of $18. I'm going to highlight those. So I got a fixed cost with the, whoop, happened to my marker. There, fixed cost of $9,202 and a variable cost of $18. And we want to know, let's see, the skateboards they sell for $125, and we want to know how many skateboards would the designer need to produce in order to sell each month to have a break even. So first of all, I'm going to think about what the cost function would look like. And the cost function, I'm going to call that cost of X skateboards. And if we have monthly cost of $9,202, that's a fixed cost, so it doesn't change. But we have a variable cost based on the number of skateboards, so that would be 18 times the number of skateboards. And I'm letting X represent the number of skateboards sold. So the revenue, how much money we bring in, our revenue function, we said that was X times P. So the revenue in terms of X would be P, the price. P is 125, so our revenue is 125X. And this question is asking us what the break-even point is. So to find the break-even point, we would set the revenue cost, the revenue and the cost function equal to each other to find that break-even point. So cost equals revenue is what we're being asked here. When are they the same? When is 18X plus 9202 equal to 125X? So subtracting 18 from 125 and dividing by 107. We got 90. Whoop, here I go again. Got 9202 divided by 107. Oh, a nice even 86 skateboards. So when we produce 86 skateboards, we're going to have a break-even point. So the break-even point is 86 skateboards. That means they have to sell 86 skateboards before they even begin to make a profit. And then we want to know the total revenue. So the revenue is is sales price times the number sold. So revenue is 125 times how many sold. So if our break-even point was 86, we have to bring in this much money just to pay the bills. So what does that look like? 125 times 86 means we need to bring in $10,750 in order to break even. Everything after that is profit. In our next example, this one has to do with some calculus skills. So let's say we want to find, this is like a minimum problem. We want to find a point closest to the origin on some random parabola x squared minus 1, right? So first of all, we know that we're looking from the origin to our point, which is lying on that line x squared minus 1. And we have the origin. So we have two pieces of information. And if you recall from geometry or algebra 2, the distance formula says that we can take the square root of x minus another point squared and y minus another point. Notice I'm using the origin here, squared, and that creates that hypotenuse if they drop to right triangle. That's this distance d because we've got the Pythagorean theorem. So x minus 0 and y minus 0 gives us this value under the radical. When you simplify that, we're looking at x squared plus y squared. But we know back here y is x squared minus 1, so I want to substitute that into that variable for y. And that term has to get squared. So squaring that binomial gives us x squared here, and then x squared, we're going to double the middle term. What's that going to be? Negative 2x squared. I'm sorry, got a mistake here. I said x squared, I meant x to the 4th. Getting ahead of myself, my brain and my pencil aren't going together. And then plus 1. And if we combine like terms, the equation that we could use to express the distance d from point P to the origin would be x to the 4th. And then combining these two, negative x squared plus 1. So that's our answer to part A. Now, do we need that for part B? I think we have to go graph next. So part B, we're going to use a graphing calculator, and we're going to graph that function, the square root of x to the 4th minus x squared plus 1. And it's going to give us that graph. I've zoomed in here really closely, and we should use the menu, analyze, and we're looking for the shortest distance, so that would be a minimum value. And you can see that I've come up with those same answers. Now, from trigonometry, I recognize that 0.707 is the square root of 2 over 2. So what did I do first? We want to make a note. We're going to either use minimum, the minimum feature on your calculator, depending what brand calculator you have. I use the analyze minimum on this particular calculator. It helped me to find that my x value is about 0.707. But like I said, I know that that's the square root of 2 divided by 2. Let me just verify that for you. Square root of 2 divided by 2 is that value 0.707 on our graph, see? Okay, and then I can substitute that value for y. So we're going to get go back to here, substitute this. Got to substitute this into x squared minus 1. So square root of 2 squared minus 1 gives us negative 1/2. And then I can know this. So looking at that picture again, see how there's two places, one over here and one over here? That would be minimum. And if I go back to this graph, you can think about it. This point is going to be reflected across here. That would also be a second distance that's minimized. Our x would be negative and y would be the same, right? So when we come over to answer the question, what point or points on the graph of the parabola are closest to the origin, then we know that by symmetry, there's 2 points. So by symmetry, we're going to have square root of 2 over 2, or 0.707, negative a half. And we're also going to have negative radical 2 over 2, negative 1/2, closest to the origin. Not closet. Close, or closest to the origin on our parabola, x squared minus 1. So like I said, in AP Calculus or college calculus, you would use examples like this to minimize functions and find different values where you were minimizing. So here we have another calculus or modeling situation. Rain is leaking through a hole in a storage bin at a constant rate of 6 cubic inches per minute. And the grain forms a cone-shaped pile on the ground. So here's my shape here. As it grows, the height of the cone always remains equal to its radius. So that's going to be important for us. And if the cone is 2 feet tall now, how tall will it be in 1 hour? So we want to set that up and get that ready. Let's clear out our calculator here so we can start over. So what do we know? We know the height is equal to the radius. And if this is the height and this is the radius, we also know, where did they say? Grain is leaking through a hole at a rate of 6 cubic inches per minute. So we have a rate that is 6 cubic inches per minute. And we know a volume formula, because we just saw that on an earlier example, for a right circular cone is pi over 3 r squared h. But look, they told us height equals radius. So we could adjust our formula to be volume is pi over 3 r cubed. And what did they tell us? The cone is 2 feet tall now, but we don't have feet, we have inches. So volume in inches, 2 feet is the same as 24 inches. So we want to take 24 to be our value. If we cube 24, multiply by pi, and divide by 3, and divide by 3, we've got a, let's see, I think I left it as a single answer here. 24 cubed divided by 3. Let's leave the exact answer for a minute. That's 4608 pi cubic inches. So that tells me what's happening. If the cone is 2 feet tall now, we know the volume right now. This is the volume now. And we want to know what the volume is in an hour. So we've got to go back here and use this rate. If it's growing at 6 cubic inches a minute, what would the rate be in an hour? So we know the volume now, and we want to know the volume in 1 hour. And in 1 hour, we've got 60 minutes. And we're going to multiply by the rate, that's 6 cubic inches per minute. So in 1 hour, 60 times 6 is 360 cubic inches. So in 1 hour, how tall will it be in an hour? So to find out how tall, we need the volume now. So the volume now plus the volume 1 hour from now. And adding those up, that would be 4608 pi cubic inches plus 360 cubic inches. And what we have, 14,476.5 plus 360. So the total volume an hour from now is about 14,836.5 cubic inches. That's the total volume. What else did they want to know? How tall will it be in an hour? So that's the height. Oh, well, we answered something we didn't need to answer. So how are we going to find the height? The height in an hour, I didn't read carefully. The height in 1 hour, I'm going to go back to the volume formula. Volume is pi over 3 r cubed, r squared, h. If we multiply by 3, divide by pi, and r and h are the same, you could take out that, put in this, r cubed. So r cubed is the cube root. Oh yeah, we did need this numbered then, didn't we? So r is the height. The height is 3 times the volume. Here, I thought I was doing something I didn't need to do, but I did need it after all. Divided by pi. So we're looking at the cube root. Clear up my calculator. We want the cube root of 3 times 14,836.5 divided by pi. Whoop, the divided by, let's go put this in here. 36.5 divided by pi. The height is about 24.197 inches tall. The radius is the height. So I just took my radius formula, but I knew radius was height. So the height is this total volume times 3 divided by pi. So about 24.2 inches tall. Whew, that was a hard question. Let's look at the next one here. We got a science question. Hooke's law for springs tells us that the distance a spring is stretched varies directly as the force on the spring. So, you know, varies directly is y equals k times x. And I'm going to use d for distance. And I'm going to use k for my variable, for my factor, and f for force. So I could say d equals some multiplier times the force. And we want to know how far will a force of 620 newtons stretch the spring. And they've told us that a force of 275 stretches a spring 0.2. So let's use that amount. If we know 2/10 is the distance that a force of 275 will stretch, we need to know what that stretch factor is. So 2 goes into this 5 times 275. Whoop, did it backwards. Where are we? So 5 times 275 is 1375. So our K factor is 1 over 1375. So coming back up here, we're going to use that formula. The distance is 1 over 1,375 times a force of 620 newtons. And 620 divided by 1375 is going to be about the distance of less than half of a meter. Are we in meters? Yes, meters. About 0.45 of a meter it can stretch. So what force is required to stretch the spring 1/10 of a meter? Well, we know D is 1 over 1375 because that's our K factor. And I'm looking for the force, and we want it to stretch the spring. The distance would be 1/10. 1/10. So we can do that in our head. The force is 1375 divided by 10. So that force would be 137.5 newtons. Need a force of 137.5 newtons to stretch the spring 1/10 of a meter. All right, this last thing we're going to do will be a regression equation. So you want to stop your video and go to your graphing calculator and make yourself a table that has the data from this chart here. So if I'm going to look at 2005 as my first year, and we'll put up here that this is the years. So I got the first year, the second year. T equals 1 corresponds to year 1. I'm getting that from right here. Create a list or spreadsheet with T equals 1 for 2001. So we're going up to what? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2. Let's see. 3, 4, 5, 6, 7, 8. And then go back up to your B column, and this is going to be dollars. So up here, we're going to put in 10.01, 10.86, 11.55, 11.18, $10.60 or $10 billion, 10.69, 11.07, and 11.82. So we got the years going in order: 6, 7, 8, 9, 10, 11, 12. Okay, and then I want to go to the next thing, which is we want to create a scatter plot. So on my Inspire, I can say Control Insert. Whoop. I can do Control I, and I want to look at the data and hover over this and get years on the x-axis and billions of dollars on the y-axis. That kind of looks cubic to me, doesn't it? So we got to choose a regression equation. And part C says we're going to get a linear equation, so we can go menu, analyze, regression, and if I choose linear, it won't let me do that one. Menu, analyze, regression. Oh, something's wrong with that. Menu, analyze, regression, cubic. Okay, too many arguments. Let's go back to the table. Oh, that's why I didn't match it. Ah, important, huh? Try that again. Menu, analyze, regression, linear. There we go. On the next screen, I'm going to write that down. Oh, that's number 4. Okay, so on this screen, we'll write that down. So our linear equation .1257x plus 10.4068. So that's this one. And then the cubic equation, can undo that one. Menu, analyze, regression, cubic. And that's this one. The cubic equation is 0.0489 x cubed minus 0.6659 x squared plus 2.6932 x plus 7.9057. Now on the Inspire, I can grab that and hover and move it over so that I can read those. So example for the 4th step here, it says use our model to predict the bottled water revenue for 2018. So if 2012 was year 8, then 2018 is going to be year 14. And then I would have to substitute my equation. So we'd come over here and enter in that equation, 0.1257x plus 10.4068. And then I could go here and evaluate it for year 14 and get 12.17 billion. $12.17 billion in water sales. And then the cubic turns out to be 49.28 billion. I got bells and whistles just dinging all over the place. My computer and my cell phone. Okay, we can't live without them anymore, can we? 489x cubed minus 0.6659x squared plus, whoop, I threw a 3 in there, plus 2.6932x plus 7.9057. Hopefully I didn't do anything wrong there. And then evaluating that regression equation for year 14, right, 49.27. So now, last question. Which model would make sense in this scenario to you? So what do you think? I thought about, to me personally, I believe the linear makes more sense because the water industry is a pretty slow growth industry. It's not going to grow exponentially like a cubic function does, especially because it depends on the economy. So we could say that's something like linear because the water industry is slow growth, is a slow growth, and it depends on the economy at the time. If you have other opinion, if you defended it, you might have a different outlook. To me, a cubic is exponentially too fast. I'm going to put fast in quotes. So here we are at the end of Unit 1, Pre-Calc. Welcome to Pre-Calc and our year. Ready for a test. See you next time.